Bismillahirrahmanirrahim. Allahumma salli wa sallim ala Sayyidina Muhammad. In the name of Allah, the All Merciful, the Most Merciful. So we are starting this video on indirect observations, which is part of the section on ayah and belief. So we're gonna cover them in a kind of traditional approach. Definition first, an example, we generalize after, we address then how it may or may not help the strong truth. And finally, I will add just add some notes on some of the current words that I used. I didn't want to add some timely events, but since they are so present, I'm gonna just address them very quick to clarify what's happening. So we are talking about indirect observation. So in the process of acquisition and use of belief in the hope of getting our ultimate goal, which is value, we are here in the sources, indirect observation. Last time we covered direct observation, and next time it will be transmission, anything that goes from somebody else, that any source from somebody else. So here, just to recap, a system is a group of, as we defined it in this channel, is a group of nature element delivering a function within a set of environment. It may take some events as input and may deliver some events as output. It may itself be made of multiple subsystems, that is, sub-functions. So here an indirect observation is an observation that made through a system. In other words, the system is the one that is exposed to the occurring event, as opposed to the direct, where it is your body that is living through the events. So such system in this context is called measurement tool, and a quick example is when you want to know your weight, you don't measure yourself your own weight because you know it's not accurate, so you use a balance and a scale, and you just standing on it, you expose the measurement tool to your own event, which is the weight here, and it gives you the measure of it. So why do I have a specific video for systems? I do that because they are everywhere, so they are used for kind of to measure, to get information on the world for almost everything. So whether basic to complex functions, from complex information from space, dimensions, to weight, to time. You must probably have a watch around your wrist. Temperature, light intensity, and a bit more complex, so speed, function of spatial, pressure, sound. I'm using a mic right now, and if you can also add further information. Typically, try to figure out how many frequencies you have in a given voice. Same image, the camera, or you are all used to it, and light spectrum here is basically the scientific name for color, and this definition can also go into the non-visible range of electromagnetic waves, which are usually called light. You have all the measures of electricity, and all this can be integrated in even more complex systems. Typically, micro electromechanical system is it could be any of these sensors, but put into a very small component, electronic component. So they are almost everywhere right now with computers and phones. And this tool typically is absolutely full of sensors, not just to measure something, but to even function themselves. It's full of them. So what are these observing systems in our quest for the ultimate goal of strong truth? How can they help us? So to explain this, we start with an example to explain their principle, at least to understand what they are, or how reliable, to get an idea of how reliable they are. Let's go over the example of a spring scale. So basically, it's a system that allows you, as long as you hang the weight on the hook, it gives you the weight very quick through this arrow. So it all starts from nature with a few rocks that contains some ore, some iron ore. You take that, you break them out, you burn them with coal and other resources to get steel. The steel is forced into a hole, hot steel is forced into a hole, it's called extrusion, and it gets you a bar. and this bar can be bent, simply pushed, mechanically pushed to get a coil, and on the edge you put two hooks and you get the spring. So that's where we start from, this spring, and we're just gonna observe a few things about that spring and see how we can turn that into that scale, and you have a clue on the pictures as you can see. So first step, you put the weight on the spring and you look at through your eyes, you see that it extends, and when you remove that weight, it extends in length. When you remove that weight, it seems like it comes back to its original shape. So that's a first observation that starts the whole process to get a measuring tool. So just to verify that, you're going to use another system, a measure tape typically, to get the length before and after, to check that indeed it came back to its original form. So that's the first two observations, and already you can note that, and it's going to be very common to design a measuring tool. You're going to need another tool to add to support information, and when you have a flow on one tool, it will have an additional contribution to the flow of the future tool you're building. So now that we saw this extension of weight, we want to know more about it. Well, how we want to know typically how does it extend compared to the weight. So to know that, you change the weight. You give it typically here 5 different weights, and you measure the 5 different lengths. So here 0.5 kilogram, 1, 2, 3, 4, and you get this length 30 millimeter to 44 millimeter, and that's at this stage that you already notice something very curious. Whenever you add 1 kilogram, it systematically adds 4 millimeter of extension. This is the behavior of the spring, and this regularity we don't expect at first to have such a property to occur. Whenever, no matter which kilogram, no matter which weight you put, it will the extension will be 4 millimeter per kilogram, and that is a very curious thing to observe, and it's these kind of relationships that initiate really the birth of a measuring tool. And it happens that, as a note, nature seems to obey systematic rules everywhere. We will come back on this when we go over very quickly nature. Some rules are more complex than the other. Here, this one where you have a nice, it's really like purchasing an object. The more unit of that object you buy, the more it will cost, and it's just a multiple of it. So this is called usually linear, and there is a bit more complex relationships that occurs. Typically, some relationships can involve change a parameter. It depends on the change of another parameter. This kind of thing. But this time, this linear relationship here is what we are going to use, and for this is the fourth step, and this is the main step. This is really the birth of a measuring tool. Instead, up to now, instead of focusing on the spring, which is we put a known weight and we get the extension of the spring, we learn about the spring behavior. We're going to switch our approach. We don't care anymore about the spring. Now that we know every kilogram you get 4 millimeter, we don't care about the spring anymore. We will focus on the weight. We give it an unknown weight, and since we know how much it extends given a weight, we can calculate the weight. And here, with this approach, we really leverage the very natural relationship that we identified before, and ultimately it gives you this fourth step. You start with the unknown weight. You measure the length, since the spring has extended. Typically here 38 millimeter. You can see in the previous picture that 38 millimeter is it's between here 36 millimeter, which corresponds to 2 kilogram, and 40 millimeter, which corresponds to 3 kilogram. So basically it's 36 millimeter, 2 kilogram plus the 2 millimeter, and for every 4 millimeter we have 1 kilogram, so 2 millimeter is half of that, so half of 1 kilogram, which is 0.5 kilogram, which ultimately you get a final weight of that unknown weight that you get 2.5 kilogram. So here we just basically made the measure with this new relationship that we identified. So there is just one last step to turn that into a fully our our system or goal. So typically we add a visual indicator, hide all the details except what is except the input, the hook to put your weight on, and the output, which is the arrow on the scale. So here to get to this level, to this final ready to use tool, we have three elements to add. The first is the spring, and it's always the case. The core measure is part of the has to be there. It's the ones that systematically make the measure for you. It's the relationship that comes from observations that we build that will give the true value you are looking for. To that core measure, you add some support to have something that is usable. For example, here instead of having you measure the length of the scale, we made an automatic way to measure that. Typically, we put a string that is attached to a gear, and the gear size is defined so that the arrow, when you put 3 kilogram, the arrow goes to 3 kilogram, and with this, thanks to that linear relationship, you get the arrow that will always face the right weight according to what you put here. And finally, the third part, which is typically anything else. So most of it is basically cosmetic: the box, the color, all the words and everything. No matter how good it looks, it plays no role in the actual value of the system, except maybe at best you have structural resistance. It protects these from being broken. That's it. So that's our system end to end, and that's all the step that was required to get them. So we have for more complex system, we're gonna use way more complex natures relationship, but it's always the same principle. Just before we generalize, just cover a few cases of what may happen with that scale we just built. The first one, you give the scale to your friend and he puts a 20 kilogram bag of potatoes on it. So here many things can happen. If the spring does not come back to its original shape, depending on the size of the spring, it may be permanently strained. Basically, it was extended and above its what we call elastic limit. So basically, the scale is broken. The spring has been completely damaged. And up to now we haven't noticed that because we didn't go above the 4 kilogram that we tested. So this kind of cases is very common with any measuring tool. If you go above the testing range, we call that error extrapolation, and basically the number you get is really wrong. You can't rely on it. First. Second is since our scale, the front here only goes up to 4 kilogram. If you put 20 kilogram, it will do as many turn as the length of the string we have put inside, and basically once the maximum length is reached, the arrow cannot go any further. So you have a number, but you should absolutely not rely on it to get your weight. So here what basically happened is a hidden limit has been introduced by a human in the design of the system. So the length of the string, and basically this you don't see it anywhere. It's not written anywhere on the box that the length is that much. So there is a hidden limit that may trouble your measure if you go too far. So really human design here that plays a role. And finally, your friend goes even further. He puts a 200 kilogram car part on it, and here the spring cannot take that load. There's a limit, so the scale indicates 0 kilogram because the whole thing is broken, and so you can't rely on it. Just to show that nature has its limits as well, no matter the system. Next come other examples. If you put a weight on 0.5 kilogram, a weight of 0.5 kilogram, and a weight of 0.500, you add 1 gram typically. What you will see is that the arrow seems to be pointing exactly at the same angle. Your eyes cannot figure out that you are. It's basically the same with the same 0.1 millimeter distance where the arrow is pointing. So you can't figure out the difference between, with that scale we built, you can't build, so you can differentiate between the two weights. So here what happens is we have reached a limit of accuracy, what is usually called the limit of accuracy. So here it's the same as measurement limit that we covered in direct observation, with the eyes, with the ears, how much you can, how much detail you can get, you can know about the event. But here, for weight, typically if I give you 0.5 kilogram, I don't tell you it's 0.5 kilogram, you're gonna suffer to, it's gonna be very hard for you to figure out exactly that it's 0.5 kilogram. So this scale is already way better than human at measuring weights, yet it has also its limits. 1 gram it can't differentiate, and usually all the systems have this kind of limit of accuracy. Next example is on a hot day. If you use the scale at higher temperature, there is another natural law where the steel expands in volume just because of temperature, and that will make the spring give extend differently according to how it has expanded in volume. So for the same weight, you can have different value according to the hot day or cold day. And so here again, there's something happening. Environment is always here, always plays a role. You're not outside of the environment. You're not outside of the world. You're not outside of the environment. It can always interfere with anything that you do. So it's to the same limit as a direct observation. And final what if case, if the spring you happen to use comes from a special place where the ore was extracted, that contains specific materials. I don't know, somebody put some gold, put some other materials in it, and after the molting process, after the extruding process, you happen to have that spring that contains other things that hasn't been filtered out. Well, the measurement can get wrong and can give a very different behavior, especially if there's a big defect that bypass quality tests. So here, just these scenarios may highlight that. Sorry, this scenario highlight that the entire history of an event matters, and the challenge is that nature and also humans are very diverse. So if you outsource, the tool is basically you outsource some of the observations to somebody else as compared to a direct observation. So all this diversity may cause things to go wrong as well. And also, if there is another human life model to account for. So we have to be mindful of this. So to generalize, what is a measuring tool? Measuring tool figures out a measure by observing its role in significantly observed existing natural relationships, and what happened with the spring is actually it's the same principle for every single system I listed before. For typically a watch, you have a quartz inside that if you put a little tension around it, it will vibrate at a very regular time, and this regular time is the one that is used to set the clock, to run the clock. So we flipped again, we saw something. When you have a watch, you don't care about the quartz inside. You only use its property, its interaction with the world. So that's another measure, and there's the same for everything else. Actually, it's always a natural law that powers it. Second element is a measuring tool is the result of a sequence of direct human observations that are outsourced to. So it's really fundamentally a human thing always, and it's not because it's a machine that it's impartial. And the thing is, a lot of the observations to produce them are outsourced to its resource extractor, to its engineer, to its engineers, those that design the thing digitally, and then to its producers that make it into a real life usable thing, and then the distributors and the maintainers. Everybody here are agents that may interfere as well with the system along its life cycle. And finally, last element, an indirect observation shares the same environment awareness limit as the direct observation. The only difference is the measurement limit. The second limit we covered in the last video. Here it may be different, and they are used because they are different. They give usually better accuracy on some events. So we can now come back to our main question, which is trying to get an idea, a strongly true belief. So here, as you guessed already, an indirect observation-based statement cannot be a strong truth because it entirely rests upon observations, no matter the system, no matter how good or how complex it looks. So it shares the same inability to derive strong truth as the limits we covered last time. Just here as an important note, it's also one of the reasons I made this video, is a system is not because it's a system that it's not that it's impartial, that is independent of everybody. A system is fundamentally a human action, and it can be viewed as a set of typically, if you want to model it, a set of fixed human decisions and actions. But to use one, you will, and to use one while trying to make sure to get to the strong truth, you're going to have to consider it as thoroughly as human transmission, which is the next chapter, something that comes from other humans, some knowledge, some source that you get from other humans. That's it. Just as a note, advantages and drawbacks of these systems, very quick, now that we covered the strong truth. So they have multiple advantages. They can allow us to perceive the unobservable, typically the infrared light. Usually you can't see it with the eyes, but with special material, special interaction, you can put that into and build. You can use that to build an infrared camera, and typically to see at night. They can also allow us to see to get information on inaccessible place, typically in distant space. You can't go to a star and get some material from it. So instead of that, there's natural relationships that occurs with light. Some components absorb some part of light, and these may characterize how what component is in a star, and just by looking at light that comes to Earth, you can figure out what are stars made of. So really inaccessible to measurable. Third advantage, of course, is the high accuracy. Typically, the weight with some of the best scales, you can go down to 1/1000th of a milligram, so really small. They also don't need a human resource to operate in most cases. In a lot of cases, sorry, and this solves many transmission questions, as we'll see later. Finally, in terms of drawbacks, so as I mentioned, a lot of observation are outsourced to somebody else, and that is we have a part of history that we don't know, and that is really a source of incertitude. And the second element is more like the more observation it relies on, the more it has a chance to be wrong, since you're making more stronger statements. That's the second. Before we go on transmissions, just a note on a few words that are common. I didn't want, as mentioned, to introduce words that are time that belongs to a time. These words typically I don't like. Digitalization, automation, and artificial intelligence. These three expression. It's product of our time, and I don't know how long they will last. But since they are omnipresent, they are everywhere. We just mention how it relates to our case here, and most importantly to strong truth that we're trying to achieve. So digitalization, so it's basically turning an analogic signal to a digital one. Just to give a general definition, a general approach. From a natural event, you transform it into electric signal. You simplify it into a list of values and transform it into code of 0 and 1, where 0 and 1 are electric signals. So basically, instead of an event, you get a code, a number code. To give an example, to be more clear, for example, a voice. A voice is a pressure wave that it travels through the air. It's defined everywhere at every point of the air, at each instant, and it may take in almost infinite range of values. That's typically what we call an analogic parameter. And if you want to save this, to turn that into something that you can share with other people, you want to select information from it, and that's the very idea of digitalization. So a microphone will detect a pressure wave and convert it into a signal. So here the wave will move a membrane that will induce some current. It's some example of microphones, not all, that will move a circuit into a magnetic field that generates an electric signal that really looks like the pressure wave at one point only. And then you will only select the pressure every typically the typical value is 44,000 times every second. That's what the ear can hear. And then you only select a few set of amplitudes, like a super loud to no noise at all, 0 to 19 decibel. With this limited set of value, you have turned already the whole signal, the whole complexity of the analogic signal into a limited set of numbers, and now you can turn that into a code. And it's turning into a code, it means typically it's the same operation as putting a words on some event. You're really just encode it into, instead of saying 25.2 decibel, I will say from now on 00010000011, and that's the digital format of it. Why would I turn into 0 and 1? That's because it's really good for it's not good for humans, but very good for electronic components, and it allows easy communication between different components, different typically mic to the screen. And basically, to sum up, digitalization, if you have followed up to now, is about turning real events into communication message by encoding into a list of digits. So it's a way to communicate simply. And the meaning of those numbers is given by humans and only known by them. A machine does not know what those zero. The system does not know what those 0 and 1 mean. It's really humans behind that will use the systems that will know how to interpret them. So this language is complex for human, but very good for electronics, and ultimately it allows only a communication system to system without apparent human interference. I say apparent because in future perspectives of this section, we see that things are a bit different. So here, ultimately, digitalization, all this pipeline is relies on direct observations. Systematically, you use a microphone to turn things into an electric signal, and then switching to 0 1 is basically a communication. Really, it's just a message, turning things into a message, and this absolutely won't help anything whatsoever to get the strong truth. No matter how this is useful, you will hear it everywhere to turn things into digital format and treat them in that way. So that's the first idea. Second idea is automation. So here, using specific natural relationships to deliver different functions. So here in the nature, there are events that allow you to generate movement, that allow you to have a support for symbolic operations, reasoning operations, that allow you to store information in a symbolic format as well. So all these are used to make a system work instead of human. And there's two main examples that are super champion of the last century, really. The actuators and engines, all that allows to convert energy to movement. So fuel combustion of your car typically releases an energy that moves a part of the engine when you just burn the fuel. There are plenty of others. We're not going to go into detail. Piezoelectric typically is a material you put electric tension around it, and it changes shape and that allows you to control its movement. And the second champion is a semiconductor system. So it's materials that whose electrical conductivity is between conductor and insulator, and by combining these materials and a few operations on them, you may reproduce a symbolic passing state 1 and a blocked state 0, where there is a signal, there is no signal, by playing between these two properties. And with this you have the representation of the 1 and 0, and as mentioned, 1 and 0 in digitalization, it's you can kind of represent almost any event, any voice, any kind of sensors, anything you use in your computer. And also, if you arrange those material in adequate manner, you can make operation on these numbers. Typically 5 plus 3 plus 5 can be done by a few combination of layers of material symbolically, and you get this. Each 0 is no electrical circuit. Each 1 is you have no electric tension, and each 1 is you have electric tension. It's really a symbolic representation of those numbers. So if you can do basic numerical and also logic operation, you can basically do a lot of reasoning capacities, and it is typically all that you use on your computer, all that is done by the computer. So ultimately, automation is fundamentally human design as well. Here we are looking at natural relationships through observations, the same way as measurement tools. And it's even more human, bigger human contribution, as the automation aims at not only measuring things but also performing actions in place of humans. And ultimately, automation, you hear it everywhere, because you can do almost you can improve capacities, the overall capacities, almost plenty of tasks, calculator, moving heavy objects, and so on. Second big advantage is there is no body limits, as there is no actual body involved in the operations, at least in the apparent. Here again, we'll come back to that. And for our question, automation will never, again, since it relies entirely on direct observations, it will never be a support of evidence to get any strong truth. So that's the second automation. And the third one is also super popular, even more these days, but don't know how long it will last. What they call artificial intelligence. So here it's various attempts at identifying relationships in nature and human history by way of automatic mathematical calculation. That's where you have the difference here. It necessarily takes as input a set of observations, whether direct or indirect. So here it's all about, instead of the automation where you say everything, you observe and organize everything to work in a very specific way. Here in AI, you allow some freedom on how to organize a solution, how to understand a natural relationship, and that typically, since the exact what you do is basically define the objective in a mathematical way, and the exact solution is derived by a calculation, and it's not you. And the calculation itself, the formulation of the base engine of an AI system is usually kind of a clear formulation, but the ultimate solution becomes complicated. Here it ultimately allows bigger range of automation, as you can do more reasoning tasks, since a machine can try and figure out things on itself by considering way more information that you can. Also, it can predict things a bit better, since it uses more history of data. Ultimately, it will more history of information. Ultimately, it has more clues on what things happen, but it's not always working. You have to find the right parameter. The disadvantages is that in the process of development you have to make many decisions that may reduce the final coverage of the solution. Depending on what you give as input, it will adapt to it. It will mathematically rigorously adapt to it. So really, it's fundamental to define the right observation as input, and of course, as any observation, it's not perfect. And also now these days, the mathematical calculations, there's many versions of it, and the ones that are super popular these days they don't provide always a clear answer on how they work out the relationship between things. So ultimately, no matter how much you hear about it, it relies, and it always relies systematically on direct and indirect observations to learn from, and that cannot be a base for strong truth. So just these three expressions quickly covered, so they're not going to change anything to what we say. So that's for indirect observation. So inshallah in the next video we start transmission, so anything that we receive from other people.